So again, the thing we learned from the video this morning is anytime your differential equation is a constant times your original quantity, that's an exponential function, and you can use that shortcut. If the initial condition is P, we can jump right away. Well, if you want to, he was saying you could jump right away to this. So you could use the shortcut to jump right away to this step. If you didn't want to use the shortcut, well, then we have to separate our y and our constant on one side, just like implicit differentiation. That way we can take the integral of both sides and solve it. So this is a reminder that you can always do this if you forget the shortcut. But you could go directly to this point. And then if the initial condition is P, well then that first value of C is always your initial condition. So it would have been okay in this question to go directly to writing this out as a shortcut. However, if you wanted to do all of the work and show it right from the beginning, you separate your variables, integrate separately, and solve from there. So we'll see word problems that look like this. A colony of bacteria is growing at a rate of dB dt equals 3e to the 0.5 t. Okay? If initially there were 5 grams of bacteria in the colony, how many grams will be present in 10 hours? So first of all, I take a look. Does this match my exponential form? Doesn't look like it, because it's not my rate of change isn't a constant times b. Okay? But we can still work through this. So if I want to solve for b, and I don't have to separate on both sides here because there is only one variable in my original equation. So I can just integrate like normal. The integral on this side is just going to be b. And the integral on that side, well, integral of e is itself, but we have to divide because of the chain rule, and we have a plus c. And we can solve for c because we know our initial value when time is 0, our initial value is 5. So that allows us to solve for c. E to the 0 is 1. 3 divided by a half will be 6. Move that 6 over to the other side, and you will get c is equal to -1. Now that we have our equation for b, how many grams are present at 10 hours? We plug in 10. Of course, this is calculator at this point. And we have 889.479 grams. Can we look at our question? Need to include units if units are involved in that question as well. So be careful with that. Got my 3 decimal places. Just trying to think. Are there any places I would go more than 3 decimal places? I would think if my answer something like this, I probably would go 6 decimal places. Because these first 3 zeros, if I stopped at 3 decimal places, do you see rounding to 3 decimal places would be this? That doesn't seem very accurate in this situation. It seems like those first 3 zeros, we need some more digits to be more accurate. I think in that situation, I'm pretty sure that the AP exam would avoid that situation at all costs. But in this situation, I would go, if I was rounding, I would round another 3, just to be seemingly accurate. Yes. Does it only use the metric system? I don't think so. Like, you could get a question in feet. Will they ask you to convert between feet and centimeters? Probably. Like, do you have to memorize those conversions? I don't think so. But they could give you any units. I think overall, once you get to higher level math, there's an understanding between scientists and mathematicians that the imperial system is a better system than an arbitrary system based on the measurements of king's appendages. So, yeah, I think you'll see more grams and more meters. But because AP is used across the world and there's a lot of AP courses in the United States, you'll probably see a lot of textbook questions and stuff still using feet and inches. Because it's still used a fair bit in the world. Number of bacteria in a culture increases at a rate proportional to the number present. So at this point, we've got our shortcut. We know that dB dt is proportional if B is our variable for bacteria. So we can go right away to y equals CE to the KT. I don't know if you remember this formula from grade 12 pre-calculus, but we didn't use K and we didn't use C. Do you remember in grade 12 having questions with P and R, the PERT formula? It's basically the same thing. Your initial population, your R is your rate. Now we're using K. So we don't know the initial population, but we do know that the number of bacteria was 600 after 3 hours and 1920 after 8 hours. So we could get an equation here with 600 after 3 hours, and in that equation we could solve for our initial condition, and we could also plug in the 1920 for 8 hours, and again, here we could substitute in that this y0, the purple box around it, gets substituted in for the y0 there, and it creates an equation where we just need to solve for k. So e to the 5k equals 32, take the natural log of both sides, and we get k is the natural log of 32 divided by 5. Again, it probably makes sense to store that value into your calculator. Exponentially catastrophic. And now that we have our k value, you could solve for your initial amount. Because you know after 3 years, it's going to be 600. Now that we know our k value, we can find out that our initial population was 75. So again, taking what you know, given 2 pieces of information, will give you 2 equations, and here we had 2 unknowns. We didn't know k, and we didn't know y naught, or the initial condition. Substitution, let us solve for 1. Plugging that back into one of your original equations lets you solve for the other one. Now, we want to solve when will this equal 120,000. Of course, you could use your graphing calculator and graph both of these. That is one way if this was a calculator question. You could put this into y1 and this into y2 and find out where they intersect. You just have to be careful that you know your window needs to show this straight line at 120,000. Okay? But if you know a little bit about your window, you'll be able to find that. Other than that, though, you could solve this with logarithms as well and get 10.646. So you have that choice because it's a calculator question, how you want to solve that. You could graph both sides and find out where they intersect, or you could use logarithms. You should probably try both ways before you get to your exam so that you're sort of like pick a way that you feel is faster. Newton's law of cooling. So an object gets heated to a certain temperature. We'll call it U0, that's our initial temperature. Then at time 0, you take that heated object and we bring it into this room, place it on the table. Hopefully it's not too hot that the table starts to burn. I'm not bringing in some super hot metal bar. And it begins to cool because the room is cooler. We know this is going to happen. And eventually, it should cool down to be room temperature. It is impossible to put something in a room and watch it freeze. It can't get colder than the room. I guess if the room was freezing, it's possible to watch it freeze. But you bring something hot into a room, it will come down to room temperature. You bring something cold into a room, it'll warm up to the room temperature. That is always the case. Okay? So what we have is the following relationship. The rate of change is some constant, the function minus t, and t is the room temperature or the ambient temperature. We can solve this differential equation. So again, what we're going to want to do is we're going to want to get everything with u on the side with du, and everything else on the side with dt. Integrate both sides, and we get a natural log absolute value u minus t equals kt plus c. And solving for this gives us the following equation for u. Yeah. So at time is 0, we We have our initial temperature. This allows us to solve for C. And that's where that substitution came in. So an object is heated to 90 degrees and allowed to cool in a room with a constant ambient temperature of 20 degrees Celsius. If after 10 minutes the temperature of the object is 60 degrees Celsius, what will the temperature be the temperature after 20 minutes? So it came in really hot at 90 degrees. 10 minutes, it reduced to 60 degrees. In another 10 minutes, what will its temperature be? So here's Newton's law of cooling that we figured out from previous question, and plugging in the values that we know. The initial temperature was 90, the temperature in the room is 20, and we can plug in 60. This would allow us to solve for K. So rearranging, using our logarithms, we solve for K, and again, we have to remember all of those decimal places. Especially in exponential functions, rounding early makes huge differences in the answers. They've actually done, I took a course in university on how calculators round, because calculators remember a lot of decimals, but they still round. And they can show you that you can use some exponential equations on your calculator, storing the digits all the time, never rounding early, and your final answer will have no digits that are correct. So even your calculator that remembers beyond the digits that it sees, rounds, and it eventually has to round somewhere, because it only has so much memory. And it's been shown that you can do certain equations on your calculator that when you finally push enter, even though you haven't rounded, every single digit is wrong in your final answer. Which kind of blows your mind, because you trust your calculators, especially if you're not rounding, that they'll be right. So in that course that I was taking, they would say, okay, you've done this much math with your calculator. Which digit is the first one that's wrong? And we'd have to figure out, oh, if I did all of that math, the first 3 digits we can trust, but after that, it's just gibberish. But the calculator is still doing calculations with that. And the more stuff that you do with your calculator, the more inaccurate it comes. Now, we don't do any equations that ever comes into play, but it is interesting. So, we keep all of our decimals. We now plug that in. We can solve when, we can plug in 20 minutes, time is 20, and solve for there. I feel like I should have used 25 minutes instead of 20, so you don't get confused. This 20 here was the room temperature. This 20 is the time. So, when we're figuring it out at 20, I'll put a purple box. This is the 20 that came from the 20 minutes. And this 20 that's here, right, that comes from the ambient temperature. Sometimes you use the same number and you look at it later, you're like, did I replace both of those with my time? Or why are those 20s both there? One of them was your ambient temperature from your initial equation, and one of them was your time.